So the topic of my talk is microbially induced sedimentary structures in clastic deposits from the Archean to the modern time. Oops. Yeah. This here is a view into the modern tidal flats of the North Sea. And we get the impression that all those sediments we see are composed of sand. However, if we take a magnifier, we actually see that the sands are colonized by a great variety of benthic microorganisms, of which, from the perspective of a geologist, benthic cyanobacteria play a major role. And that's what I'm going to talk about the next few minutes. So here are two examples for benthic cyanobacteria. This is the species Merismopedia punctata. It forms pillow-like clusters of round-shaped cells that are firmly attached with their extracellular polymeric substances, abbreviated as EPS, to their substrate. This here is Microcoleus tonoplastis, which was recently renamed, which is a filamentous form. It forms elongated chains of cells. This organism can become quite big and is actually the reason for that in the older literature specifically, people call those microbial mats algal mats and blue algae and so forth. That's because people thought it's actually an algae and not a cyanobacterium. So when such microorganisms initially start to colonize a freshly deposited sediment, they form so-called biofilms around each individual grain. So here you see the surface of a quartz grain, and this quartz grain is completely enveloped by this organic film. Biofilms are composed of the single cells themselves plus their EPS. Those EPS are mucilages that are very adhesive and that have certain functions for the microorganisms. For instance, they help the organisms to attach to surfaces. They buffer salinities to fight osmotic changes in the cell. They transport nutrients, and they also serve for communication between different cells within a biofilm. Now, if such biofilms continue to grow over several months, they form finally large-scale microbial mats. This is what we see here. Here's a knife for scale. Microbial mats can become very, very thick, several centimeters thick, and they can have square kilometers in extension. And clearly, if we have a microbial mat system like that, we can imagine how a microbial mat can affect sedimentary processes in clastic systems. So let's imagine how microorganisms colonize a sandy sediment that's moved around by waves and currents. As you can imagine, it's very dangerous to be very small in such a situation. So the question is, how do prokaryotes survive physical sediment dynamics? So you all know what physical sediment dynamics is. It's erosion of sediment, or it's deposition of sediment. And then there is latency or stasis, which is a time frame during which the sediment is not moved around by water motion. So it is completely quiet. The microbial response is very much tailored to each specific sediment dynamic situation. During times of erosion, we can observe biostabilization. When there is deposition of sediment, we can observe baffling and trapping of the organisms. And then there is growth as well as binding during times of when the sediment is completely quiet. So let's take a closer look to that. This is a diagram that looks complicated, but actually it is not. It's composed of 3 arrows. This arrow here indicates an increase of intensity of erosion. This arrow here shows an increase of intensity of deposition. And this arrow here shows increase of latency, so the time when the sediment is quiet. The orange rectangles indicate various responses by microbiota to specific dynamic conditions. So let's start what happens during a latency. What we observe are two things. The first one is binding. This is a vertical section through a microbial mat. You can see here the filaments of microorganisms. They form a network. It looks a little bit like a carpet. And in between, we see some sedimentary grains and EPS and so forth. So the first step, binding, is that microorganisms move actively through a sediment. They communicate with each other to form a very coherent microbial network. That's the formation of a biofilm, which is a highly constructed microbial community where each member depends on the next. There is an interlocking of metabolic activities and so forth. So those are complex microbial societies. So that is binding. And of course, binding takes place when the sediment is quiet and there is time to configure such a biological construction. Then, of course, we can observe growth. This here is a vertical section into a modern tidal flat. We see here ripple marks, clearly the ripple valleys are filled in by biomass of microbial mats that grow in the valley specifically until finally the microbial mat surface is completely planar and the ripple marks have disappeared. So that is growth. Now, very quickly, if we just stay specifically for tidal flats right now, tidal flats are in general divided into a subtidal zone, which is mostly affected by waves and currents. Then there is the intertidal zone, which is affected by the daily tides. And finally, there is the supratidal, which is covered by water only in exception, for instance, during storms or very high spring tides. Now, along such a transect, we actually can see specific microbial mat communities forming in response to the average dynamic condition. So in the lower intertidal zone and upper subtidal zone, we can see biofilms. So this is a biofilm character of colonization. You see here quartz grains, and in between the grains, here this green material, in this case, it's Merismopedia punctata. Those are little biofilms that form around each sedimentary grain in here in this area where there is a constant wave action. Let's move into the upper intertidal zone. Within few hours of calm in between flood currents, endobenthic microbial mats can establish. The main mat former here, if we stay with the example of the North Sea, is Oscillatoria limosa, which is an organism that can move through the sediment very quickly. So it forms within hours an endobenthic microbial mat. The word endobenthic means it's sitting within the uppermost 1 to 2 millimeters of the sediment. So it's really just a thin film. Sometimes the sediment is not even discolored and it needs a trained eye to actually see those microbial mats. And then there are epibenthic microbial mats in the lower supratidal zone, which are the thick microbial mats that we commonly know from our textbook. So what happens during erosion of sediment? What we can observe is biostabilization. This here is a lateral close-up view onto a modern microbial mat. This is the microbial mat surface here, and we see that a current crosses this surface. Here's a sedimentary grain sticking out, completely overgrown by biomass. Now, What we see here, not so much, are filaments that interweave the sedimentary grains. And you get the impression, well, the filaments are out of focus. We cannot see them. The reason is that they are embedded in those mucilages, which are clear and which are very adhesive. So this effect of the mucilages holding the sedimentary grains together, plus this network that also holds the sedimentary grains in position, increases the resistance of the sedimentary surface against erosion significantly. And we were measuring that in the field with our portable flume jumper. So we created an artificial current crossing different types of microbial mats in the field. And we were measuring the start of erosion with a laser instrument here digitally. And what we found out was that there are actually three main types of biostabilization. Let's start with epibenthic microbial mats. They seal the sediment completely and basically change the effect of water from being turbulent towards laminar. And we know that laminar flow has much less erosive energy than turbulent flow. So this type of biostabilization increases the resistance of the surface against erosion by magnitudes of 12. Let's move to endobenthic microbial mats. They do not have so much EPS because they're very mobile. They are actively moving with the sediment if they have to. Here, the biostabilization effect is by magnitudes of 3 to 5. Because here this network is just a network of filaments. It's not so effective like the other one for biostabilization 1. Biostabilization type 3 is a little bit different. We observe in areas where there is a constant water motion, even just a very little, that the organisms form mineral biotic aggregates. Those aggregates stay in suspension for quite a long time, much longer than sterile grains would. The reason is that they have a smaller specific weight compared to sterile grains because of the biomass that plays a role here. Now, this is important because cyanobacteria are photoautotroph. If they would be buried, that would not be good. The light would be blocked. So this is a mechanism to ensure that once the sediment is completely quiet, those little aggregates are deposited at the very least at the very top of the sediment, and they remain within reach of light. So let's take a look at the reaction of microbial mat with respect to deposition of sediment. This is shown here. This is the same microbial mat you've just seen when I talked about biostabilization. This is a Mickey Mouse sketch of sedimentary grains raining down onto this microbial mat surface. You see how the microbial filaments reach out perpendicularly into the supernatant seawater. They comb out sedimentary grains from the suspension. It's an inactive process. They don't do this actively, and they overgrow and migrate over the incoming sedimentary grains and incorporate them into the microbial mat matrix over time. So this is called baffling and trapping. And clearly it's a different behavior than biostabilization or binding. So there are two different types of baffling and trapping. Microcoelius tonoplastis actually mainly predominantly traps a different fraction of sand grains, a smaller grain fraction, like large silt to very fine sand, whereas oscillatoria limosa, which is able to move very fast through the sediment, migrates with the sedimentary surface very fast. So for instance, if ripple marks are migrating, this organism migrates with the sediment and traps incoming sedimentary grains. Why it's doing so. So how does this microbe-sediment interaction cause traces in the deposits? Now, we all know of macroorganisms interacting with fresh sediments in the modern, and they leave a trace behind. Those traces can become fossil, and then we call them trace fossils. And the very same we can do with microbial mats that, as a big unit, interact with the sediment. So very quickly, if we are in a setting where there is no colonization by benthic microorganisms at all, we have erosion or deposition of sediment, and once in a while the sediment is quiet. And the result are specific sedimentary structures, like in this case, ripple marks. So let's stay with the example of ripple marks. This is the situation in the presence of a microbial mat. Microbial mats decrease the effect of erosion, and they also affect the position of sediment. That means this must translate into the record with respect to a formation of sedimentary structures, and this is what we can see indeed in the field. Where there is a microbial mat patch, for instance, ripple marks that otherwise would have this shape have now this shape. They are smaller, they have less deep ripple valleys, and the crest to crest distance also is shorter. So we really see this dynamic situation translated into a sedimentary structure. So there are a lot of different microbially induced sedimentary structures out there. This term is abbreviated as MISS, and indeed the MISS are now a group of microbialites defined in the Treatise of Invertebrate Paleontology. There is a volume now devoted for the prokaryotes, and the MISS are in there together with stromatolites and thrombolites and lyolites and all those. So there are 17 main types of MISS arranged in this diamond-shaped graph here. Yes? Oh, okay. Yeah. And so there are different ones. Here is, those are the main agents of formation, and certain sedimentary structures are related to the main agent here. MISS have a wonderful distribution with respect to space and time. They come up already in the early Archean. I'm going to show some examples. And they made it through the entire Earth record without much change until today. So conveniently, we can observe their formation today. We can quantify their formation. So we have information to understand prokaryote evolution over time. We know MISS from river shores, lakes, playas, deltas, shelves, and so forth. So in any aquatic deposit. So how do the structures now look like? Just a few examples. Those are polygonal oscillation cracks. It's first, this term sounds a little bit odd, but you will understand it in a moment. This is a photo of a modern microbial mat here from Tunisia. The microbial mat is about 4 centimeters thick. Here in the center is a polygon, which I'm lining out here now. Here's another polygon. Here's another one, and so forth. The polygons are separated from each other by cracks that are accompanied by bulges. So each polygon has a bulge at its margin. So you see here 2 parallel bulges along those cracks. Within the crack is also microbial mat. It's just a younger generation. Such a pattern arises in semi-arid climate zones, where during arid conditions, the microbial mat polygons shrink, and if moisture conditions establish, the polygons expand again laterally, so we get those cracks moving back and forth. This is the same situation in the fossil from the 2.8 billion year old Pongola supergroup in South Africa. where we have beautifully preserved polygons of fossil microbial mat. Here you can see even those bulges along both sides of the polygon. Polygonal reticulate patterns. This here is about, 5 centimeters here. So we look down onto a microbial mat surface. We see those honeycomb-shaped pattern of ridges. Where the ridges meet is a little tuft here. Here the same situation in the fossil. We were quantifying those cells that are being defined here by those honeycomb patterns. And it's indeed the same distribution pattern of cells and crossings and so forth. Those are patterns that rise through stress situations for a microbial mat. It's not entirely clear what kind of situations that could be. For instance, desiccation effects and high salinities, things like that. And nicely here, this fossil example is from the 3.48 billion years stressor formation in Australia, which includes some of the oldest fossils in the world. This here is a modern example of a microbial mat fragment. The scale here is 1 centimeter. Typical for microbial mat chips are those lobate outlines here, embayments, and also round-shaped holes. This here, believe it or not, is a fossil example, again, from the stressor formation, where we can even see individual layers of microbial mat, which now microbial mats are composed of several layers of different microorganisms stacked all upon each other. So a beautiful fossil example here. Erosion remnants and pockets. Again, you've seen this photo before, right at the beginning of my talk. The scale is here 1 meter. You see that the surface is arranged into elevated surface parts that are planar and overgrown by microbial mat, in this case, an endobenthic type. Whereas here, those surface areas are deeper. They're filled in this photo with water and have ripple marks. So here is no microbial mat. And here the same situation from the fossil record from the Cretaceous Dakota sandstone. Here we see a planar surface, which is fossil microbial mat, where erosion has taken away microbial mat. So that here we see the barren sediment, which is now ripple marked. So let's move into Archean rocks. This here is the Niflasacha section of the Pongola supergroup. It's about 46 meters high in total, but includes 600 excellently preserved MISS, and we hope that this site will be classified as a geoheritage site anytime soon. What we see here are MISS that allow us to reconstruct tidal areas, very specifically up to a meter scale. Here's a pattern that we call multi-directional ripple marks. Here you see a field of ripple marks that have the direction from here to here. Here is another field of ripple marks that have a direction from here to here. In between are ripple marks that run from left to right. And clearly, so we have a ripple mark pattern on one and the same sedimentary surface that is sort of different. Such ripple patterns derive from an interaction of microbial stabilization, which is interrupted by episodic, very strong storm events. And here's this very similar pattern in the fossil record. This is a view of an endobenthic microbial mat. Again, you see here the mat is removed a little bit by shear from its substrate. It folded up. Here is a little bit of a mat fragment with folds, and this is what we see here in the fossil record again. So we know there is a microbial mat in each case because we do thin sections. We see the filaments in there. So that's very well established. Now here examples from the ancient lower subtidal zone. Here are ripple marks overgrown by microbial mat. again. So here the valley infilled, and this is what we see here as well. Here we take a look downward onto a microbial mat surface. Here is the edge of a microbial mat here. And here is a little microbial mat chip that was broken off. This is fringed edge here. Here the microbial mat is eroded away. Here's the same situation in the fossil. This is the edge of a microbial mat. Here it is eroded away, but here is still a little fragment sitting like this one here. And here a fossil and modern example for a microbial mat chip again. So those are epibentic microbial mats. So again, we can use, there are many, many more MISS in the area, but we can reconstruct the pongola as well as actually also the dresser formation material as being a fossil zapka, like we know from today from Tunisia, for instance. So how do MISS become preserved? Very quickly, MISS have a ternary character, meaning they produce large-scale sedimentary structures that we have just seen, but also they include body fossils of filaments and cocoid-shaped cells, as well as they create real trace fossils, which is what I like to talk about in a moment. So we talked about sedimentary structures. Now we move into trace fossils and body fossils. The latter are visible in thin sections that we can analyze with respect to optical and chemical signals. So let's start with trace fossils. Here the example of oriented grains that become visible in vertical sections through a microbial mat layer, which is shown here. Those black lines are filaments. What you see here are individual grains that seem to float in this organic matrix. The reason is that initially each grain was surrounded by thin biofilm. Over time, that biofilm becomes thicker, so the grains are pushed away laterally and until we have this very characteristic of oriented grains. Here we can see this nicely in the fossil record. It's one of a very, very typical texture that is related to MISS. This here is from the Moody's group, 3.2 billion years old from South Africa. Microsequences form simply because microbial mats protect their sediment underneath against erosion, so that amalgamation during deposition of coarser sediment, which normally takes place in a clastic setting, does not take place. So we can see certain microsequences defined by microbial mats, and we can reconstruct ancient flow velocities with this information. Now let's move towards body fossils. This is a close-up. You can see beautifully preserved fossil filaments here, nice EPS and oriented grains and so forth. So we can analyze the chemical mineralogical composition of filaments by using all kinds of technology, for instance, laser Raman spectroscopy. We can do microprobe analysis. And what we commonly find in Archean, specifically clastic material, is the following composition of filaments. The cell wall very often still contains the original carbon of the organisms, which is important. We have a carbon isotope signal and so forth. Inside the cell, very often have pyrite or hematite, as well as chemosite forming, whereas the EPS very commonly are replaced by chert, which is silica. So because there's so many textures, we now also introduce MIST, which are microbially induced sedimentary textures, which are summarized here in this graph. We have in situ replacement minerals, we have isotope signals, organic carbon that is still preserved, the original carbon, and we have those traces that I just introduced a little bit. Now, how we can look for MISS on Earth, and specifically also on Mars, which is a terrestrial planet, which includes a lot of clastic material. So the first question is, what are the characteristics for a fossil Lagerstätte on Earth? First of all, we need a paleoenvironment where a lot of microbial mats were able to grow, which is a logical first step. Then we need to have a taphonomic path that allowed preservation of the microbial mats as MISS. And finally, we must not forget that we need to be able to get to that site. If it is buried in 2,000-meter depths, it doesn't help us. It needs to be exposed. There need to be an outcrop. We need to be able to see that outcrop and large bedding surfaces, if anyhow possible. So now what do we do on Mars? So first of all, the Mars includes Archean and Hesperian rocks that have more or less the same ages like the Archean. And there are a lot of those rocks. And quite nicely, there are more Archean aged rocks on Mars than on Earth, because on Earth, the Archean record, as you know, is quite spotty. So there's an entire archive on Mars waiting to be explored with respect to MISS. And quite nicely, we have the same physical sedimentary structures on Mars like on Earth. So if we know now how those structures are modified by microbial presence, we can expect the similar structures to be on Mars as well. MISS Lagerstätten show a certain stratigraphic position, a certain paleogeography, and a certain lithology. And I'm going to show this now. With respect to stratigraphy, MISS are located in areas where there is transgression. So wherever there is a transgression in sequence stratigraphy, we can expect MISS, which is very helpful if we deal with very monotonous clastic successions. With respect to paleoenvironments, I mentioned this before, wherever is water, there can be a biofilm or a microbial mat. And clearly on Mars, there are aquatic settings abound, fossil ones. With respect to lithology, lithology is defined by sedimentary structures, mineralogy, as well as bedding character. Now, if we take a look at lithophages that include MISS, we see MISS are not the lithophages that record very, very slow water motion, if at all, that include a lot of fine-grained material, because that material would block light, which is not good for photoautotroph organisms. They also don't occur in areas where we have coarse sediment, like conglomerate or coarse sand, where we have cross-bedding and HCS and so forth, and certainly not where amalgamation takes place that would rip the microbial mats into pieces. We find microbial mats in areas where we have small ripples forming undercurrents 2 to 20 centimeters, forming rock beds that have discrete layerings with beautifully preserved environmental surfaces, so mostly composed of fine sands. So indeed, so we don't bother to take a look at successions that have amalgamated sandstone bars. We don't need to deal with fine-grained deposits, especially if there's tectonic smear causing pseudo surfaces. We need to look for environmental surfaces that have some ripple marks or anything that show us this is the original sedimentary surface. So we talked about the ecological window, the taphonomic window. Now we need quickly mention the window of detectability. Detectability defined by surface exposures, textual contrast, modification by weathering. Clearly, if we go into the field, we don't need to look for sites where there's a lot of weathering, a lot of debris. We need to look for sites that have beautifully surfaces exposed that are not affected by any recent weathering at all, so fresh surfaces. And of course, if we take samples, we need to look for rocks that are very simple with respect to composition. If the background of our host deposits is already optically and chemically producing a lot of noise, we will have hard time to identify textures possibly made by life that are nicely visible, both with respect to optics as well as with respect to any chemical analysis that we do. So here are a lot of Archean examples that we even see with having no experience at all in looking for microscopic MISS in the fossil record. So everybody clearly sees this is fine sand and clean quartz and chert, but here we have fossil microbial mat in those thin sections. So this was a rough summary of some more than two publications, but this one here is specifically for the exploration on Mars. Came out in Astrobiology 2021. It's open access, so you can read about all those things I talked about here once more. And I wrote a textbook which is available as well. I don't get rich of that, so you can still buy it, but the main thing is to read it. And so, yeah, thank you very much again for the kind invitation. It was a pleasure to be here today. Thank you.
Thanks very much, Nora, for this great talk and well, to this journey into the distant past and even up to Mars. Really great. And I think we're going to open now the discussion. So